Imagine flying drones for a living. Dave Scott uses the most modern technology in drones that he builds himself to create 3D maps of land. These maps can be used for agricultural or building purposes, or even to build dams.
So landscape mapping is using drone technology, or in our purpose, using drone technology and high-resolution GPSs to model a piece of land. We would take ground control points, we call them, with high accurate GPSs, and then take a drone and fly over this piece of land and capture high resolution aerial images. We then take these sets of data, put them into computer software, and create a three-dimensional model of this piece of land. From this information, we can then withdraw critical details such as the contours of that land, and we can then use this information and bring it into alternative softwares where clients such as architects or engineers would design on top of this three-dimensional model. So there's two main types of drones that we would use for mapping. First would be multi-rotor, which are much more accurate with precision and very easy to operate. They can take off from a 1 by 1 square meter placemat, take off vertically, map the piece of land, and then come back and land on the same spot. The other is fixed-wing drones, such as a little aircraft or a delta-shaped wing, and those require a lot more experienced pilot to operate them for takeoff and for landing, because they require a bit more skill to bring them in and land safely. But the benefit they do have for us is that they can fly a lot longer, so they could map much larger areas of land in one single flight.
So you get to play with drones and radar control planes as part of your job all day?
Correct. I've luckily been quite interested in radio controlled aircraft and that technology since I was a young child. And then through my master's degree, I was presented with the opportunity to go to Antarctica. And Antarctica doesn't have much satellite data available. And the images we do have are terrible. You can't even identify the mountains most of the time. So that's how I got into using this technology once again, and we used these high-resolution images to map the areas of land that we were studying. So I'll show you now how we do with one of our open source drones, how we would map or plan to map this piece of land here.
What is an open source drone?
So we call open source drones, they aren't sort of off-the-shelf drones that you would buy on a website. We would buy in the motors, the flight control system, the frame perhaps, and we construct the drone ourselves. And what this allows us to do is program it a bit more efficiently and add on whatever kind of camera system we wanted, or gimbal for the camera, or whatever the case might be. Whereas a lot of the sort of cheaper off-the-shelf units are very limited. The camera is built into the drone. It doesn't allow us to carry much extra weight. Whereas if we build the drone ourselves, we can build it a lot larger, and we can carry perhaps even 3 cameras at one time. The first step is to put out control points in the field, which are plates, or we actually could sometimes draw or paint the ground to give us an X or a shape which you can identify from the aerial images. Generally for a site like this, we'd have about 15 control points. So the lower or the closer we are to the ground, the higher the resolution would be of the final image. But if it's a very large area, we aren't actually needing such high detail, like we're needing to know where the roads are and that sort of thing, we can fly a lot higher, which is a lot more efficient. So we can do a lot larger area in the same flight time.
And that pattern that you have, does the drone do that automatically?
Correct. So what we're doing now is we're setting up the flight path for the drone. So this yellow line is where that drone would be flying, and you can see the direction of flight as well. Mm-hmm. And now we're telling the software what drone we're going to be using, what camera we'll be having on. Let's say we're using a Sony A7 R2. What height we're going to be flying. So let's say we're going to fly at 100 meters above ground. What flight speed, let's say we're going to be 10 meters per second. The angle, we can change the angle of flight, so we often would change the angle according to what the wind direction might be. If you're going to be flying perpendicular or with the wind.
What does flying perpendicular to the wind mean?
Flying crosswind, basically. If the wind's blowing in this direction, the drone will crab along like that.
Okay. Why do you do that?
Well, if you're flying with the wind and against the wind, you have a very slow flight into the wind. And then when you're going with the wind, if the wind's quite strong, it might blow the drone a bit too fast for the camera. And we'll be capturing every fifth image rather than every image that we need. And that then allows us to get the correct overlaps for that map.
So you take a number of photographs and then you overlap them in the computer?
Correct. So what we're planning here is our overlap and our flight path. And we would be looking at about 75 to 80% overlap and side lap on each picture. So if we zoom in, you can see that this is the actual overlapping images, and it gives an estimation of how many pictures it's going to be capturing. So if it's just a top-down map we're making, we don't need as much overlap. But if we're wanting to do a three-dimensional model, which is spatially and geographically corrected and to a certain spec, then we would need to have enough overlap and enough side lap to create this very high resolution and very accurate model. We then save this file and upload it to the drone. And then we send the drone off on its flight. It will fly all of this automatically, so it'll take off over here where we started. It'll fly to point 2, and then fly to point 4, point 6, point 8, and so on, and map this whole area, automatically triggering its camera and all of that. The next step is to take those images and put them into our software. The computer and the software is connected to the drone via a telemetry module, which is a wireless module. We can send this information to the drone to begin that mapping mission.
This is fancy equipment. How much does a drone cost?
Well, half the reason we build our own drones for certain projects is because of the price of off-the-shelf drones. We've got a variety of drones at the moment. Some of them are 15,000 Rand up to 400,000 Rand drones. Some of the drones which I'll demonstrate today, we've built ourselves, which have saved us 300,000 Rand, just because we can build it ourselves. Obviously it may not be as durable or as efficient as off-the-shelf drones, but it serves a purpose for us, and it saves us a huge chunk of money. And also if we build it ourselves, we can repair it ourselves. And spares are also a huge expense in drones. So being able to build it ourselves, also repairing obviously is a big cost saving as well. And
the software that you've been showing me, is that also very expensive to use?
Well, this sort of open source software is obviously free.
No, is this open source?
This is open source. So that's the nice thing about them. But if you buy off-the-shelf drones, most of the mapping software is free as well. But then the more advanced softwares you would have to pay for. The modeling software is obviously quite expensive. But there's also many different softwares out there nowadays, and some of them are open source as well. So you can get around that. It just may not be as easy to learn in the first place. So this map and model are going to be used for the planning purposes of 3 houses which are going to be constructed on this piece of land. What it allows us to do is get an idea of the elevation profile of this land, and also work with distances from the river. Because this is an estuary, there's critical environmental issues around it. So we need to make sure that the houses will be built within or outside of environmental triggers. So distance from the river is very important, and elevations are important. And obviously for the construction of the houses, knowing what the topography looks like is important. So once you've completed the flight, we then take out the memory card from the drone and download those images to the computer, and then bring it into modeling software, which is what I'll show you over here. So this is that piece of land which has been modeled. How it works is actually, because there's so many overlapping images, we usually work on 75 to 80% overlap. They are, for this project, 278 photographs, and at any point there'll be at least 15 photographs which can see one point on that map. The software, what it does, it triangulates those points. So this is just the first step in the modeling. We would then produce maps which show the contour data, the elevation profile. So here in this even we've got the elevation model. So red being high elevation, blue being lower. You can immediately see that this is the highest point up here, and as you progress down to the river, the color changes.
And did you tell the computer that, or did it work it out for itself from the info?
So it works it all out from the info. So we've told it that those are the accurate points. It feeds that back into the modeling, corrects all of the points that it generates. So for this model, it built 150 million points of this piece of land. And then we'll take that information out of the software into an additional software, which we'd use to eliminate features such as buildings, trees, and remove that from the model. And then we'd get a much more accurate contour map. Okay, so this would be the product, the final product that we'd use for this sort of project. So that information just from that modeling software we brought into additional software such as GIS mapping softwares. There's again paid versions and open source versions of that, which is fantastic, and the open source versions are actually incredible these days, and there's a lot of user input into those and they keep getting updated. As you can see in the background here, we've got the contours of that piece of land. These are where the proposed houses are going to be. This is the proposed dam, this is the existing house down there, and you can see very easily from the contours what that land is now doing. You can see there's a very steep cliff over here and a gentle, more gentle hill over here, and as you progress up to the road, the land sort of flattens out over here. And we've measured the distances from the high water mark up the slope, and there is our image in high resolution overlaid onto the Google Earth base map. 1 pixel on Google Earth is 1 meter in reality, whereas where on our image we've got 2.5 centimeter is 1 pixel. So additional to the top-down map, this information gives us a three-dimensional model of the land. You can move around as if you were on that piece of land to view it from different angles. And this information can be exported and brought into additional software that engineers or architects might use. So they could then draw on top of this model their houses or their plans, whatever they might want to do. And it'll be in the correct space and position. Yeah.
And they can then buzz around the house and all the topography.
Correct, yeah.
Will balance out.
That's right.
What a great job, flying drones and using 3D software for a living. Dave runs his own business, so you can contact him if you need some more information.